So here we plot the effective stresses in the cylindrical coordinates. So this is the effective hoop stress, effective vertical stress, effective radial stress, all coming from those equations we had presented previously, but precisely at the wellbore wall. So where R equals big R. So radial distance from the wellbore centroid or center to any point R, but here R equals the radius of the wellbore, right? So R equals big R, which equals this distance. Good. And what are we plotting those against? We are plotting those against theta. The angle between, where is SH max? SH max is here. Keep in mind, SH max doesn't have to be in the horizontal direction, right? I can put it anywhere, and I like to change where I put it in the quizzes and in exams. So you need to check out where SH max is. SH max is here, so theta will start from here, right? So if you're in this direction, well, theta is this angle. If you're here, theta is that angle. So we are plotting theta starting from a value of 0, meaning you are in the direction of the azimuth of SH max. And you start out from that point 0, and the angle is increasing. At this point, what's the angle? It's 90 degrees. What's 90 degrees in pi radians? You already know 2 pi is 360, right? So pi is 180, and 90 degrees is pi over 2, right? So 90 degrees is pi over 2. So at this point, you're at pi over 2. So we stop there. Then we go in the other direction. So this is minus pi, right? And you keep going until you get to minus pi over 2. And that's what this range is. And remember, there is a theta in the Kirsch equation. So just go in there and put these values of pi in place of theta, and you get different values for the 3 effective stresses, and that's what is plotted up here. And the hoop stress is the one that gets the highest. That's the one we've been looking at the whole time, and it's maximum at this value right here. The question is, where is it maximum? We already know that stresses, compressive stresses, get concentrated in what direction? In the direction of SH mean, right? So it's going to have to be maximum when theta is pi or minus pi over 2. And that's what you see here. Minus pi over 2 is maximum. Pi over 2 is maximum. So this is pi over 2. Where is it minimum? In the direction of SH max, right? So theta is 0. At theta being 0, the hoop stress is minimum. And you see, it can actually be negative. How do we know this? Because your sigma RR shown here is at 0. And what makes sigma RR to be 0? You will see in the equation for sigma RR at the wellbore wall that it's actually delta P, which is P mod minus pore pressure. So if pore pressure equals to the mod weight, then sigma RR is 0. So moral of the story is sigma theta effective hoop stress can be negative, and that's when it actually induces tensile failures, right? It's negative means it's tensile, because we're using the petroleum engineering convention where compressive stresses are positive. So tensile stresses will be negative. And when it gets negative, like I explained here, right, it's tensile. And that's your drilling induced tensile fracture. It's going to be 180 degrees apart. And that compressive failure, which we talked about previously, is your wellbore breakout, and it's also 180 degrees apart. And that means there is going to be 90 degrees between your drilling induced tensile fractures and your wellbore breakouts. So the high concentration of the compressive hoop stress leads to compressive wellbore failure, which is called breakouts. When the compressive stress exceeds the compressive strength. So for the wellbore breakout, it's failure in compression. For drilling induced tensile fractures, it's failure in tension. And as soon as it becomes negative, we just assume, yeah, you will easily form drilling induced tensile fractures. Why? Because the tensile strength of the rock, right? We've talked about different types of rock strength. We talked about compressive rock strength, tensile rock strength, frictional and frictional rock strength. So here we're talking about tensile rock strength. The tensile strength of the rock is very negligible in comparison to the pore pressures, the stresses and all, right? So just a small negative value on this can easily lead to drilling induced tensile fractures, because you think this is small, but this order of magnitude is much bigger than the order of magnitude of your tensile strength, as we discussed in module 4. And by the way, if you go plug in the values of theta into the Kirsch equations, with r being, this r being equal to the wellbore radius, well, the equations simplify to the expressions I give here at the different values of theta. So here, theta is 0. So go in there, plug in theta as mean 0. The equation simplifies to this for the effective hoop stress. And that's the minimum value. And that's what you get here. This is where theta is 0. If you go in there and plug in theta equals pi over 2, which is 90 degrees, and pi radians, 90 degrees, or pi over 2 in radians, then you have your sigma theta maximum as this. The equations look alike, right? But they are not identical. You say this is 3 times SH max, whereas this is 3 times SH min. So they are different. And I'll show those equations subsequently. So we can actually observe wellbore failure on image logs. And I talked about UBI, ultrasonic bowl imaging, FMI formation, micro imager, both from Schlumberger. And we said this has the higher resolution, but doesn't work very well with oil-based mounts. So we use these when you have oil-based mounts. So you can see the resolution is clearer here. The fatter one, as you can expect, is which one? Wellbore breakout or drilling induced tensile fracture? Just from what you had seen on the previous slides, where the wellbore breakout was wide, whereas the tensile fractures was they were very thin, right? It's a very small scale fracture created in tension. So the wide one is your wellbore breakout. So this is your wellbore breakout. Same here. I'd mentioned it has to be 180 degrees apart, right? That's exactly what you see here. If this is roughly east, well, this is roughly west. So that's 180 degrees. And do you see this line here? This faint line? Also here, 180 degrees apart. That is your drilling induced tensile fractures. So you can observe both of them on your image logs. And here, those are your wellbore breakouts, and the thin lines are the drilling induced tensile fractures. So compressive, yeah, this is basically summarizing all I've just said. And they both indicate, these two logs indicate that the direction of SH max is northeast to southwest. How do you know that? Which of these is the direction of SH max? You already know the stress is going to be concentrated. You're going to have the least concentration of stress in the direction of SH max, whereas in the direction of SH mean is where you're going to have the highest concentration of compressive stresses, which will lead to the breakout. So this is the direction of your wellbore breakout. So the question is, what's the direction of SH max? You can just get that directly from the direction of your drilling induced tensile fractures, which is here, right? So it's northeast, a small angle, right? This from north to east is 90 degrees, so this is about 30 degrees thereabouts. So you can write it as north 30 degrees east. That's the direction of SH max, and that's what's written here. So northeast, this is north, this is east, and going to the other side is southwest, right? And that's why it's written as northeast to southwest, but more specifically, this is how we're going to write it. Not 30 degrees east, or whatever this angle is, which is pretty much about 30 degrees.